Okay, let's start a lecture. Okay, check. So people in the back can hear me here? The microphone's working? Okay, good. Alright, so we'll continue on 246. I did a little bit of review on some of the common mistakes that I have seen in the past few years. Okay, and I think I've finished the majority of that. There is only one. I just want to finish that before we get on to a new topic. So the last part, I wanted to bring it up to your attention. Is to how to graphically add, subtract, and multiplying. Okay, two functions. So the keyword is graphically. Okay, the functions that especially useful when we learn very shortly, maybe a couple weeks from now, about the convolution operations. So I'll give you an example here. Okay. So let's say I have a function f1 of t. Okay, so I'll call this as the first function, f1 of t. f1 of t is graphically, it can be represented like this, for example. It's a rectangle wave. It's a rectangular wave, only exists between 0 to 2. Okay, for t between t to 0 to 2, the magnitude of that is 2 at here. Other than this area outside the 0 or greater than 2, that function is essentially all 0. Okay, this is what we call a rectangular curve, okay, a square wave sometimes. And the second function, let's say, is called f2 of t. Now this one is very similar, but just a bit of a shy in terms of the magnitude. Okay, that's f2 of t. Okay, now what we want is, we want to calculate what is f1 of t plus f2 of t. Or what is f1 of t minus f2 of t? Or what's f1 of t times f2 of t? Okay, so those are the kind of possible things we wanted to do. Okay. So let me show you maybe the first one here, okay? And you can practice yourself what's a subtraction and what's multiplication. Now at this stage, I would highly recommend, actually I would try, if I can mandate, I would mandate it. I want you to follow procedures very exactly, okay? Especially when it comes to the graphically solving a certain question. Follow procedures basically means, okay, like what I just did, when you draw an axis, draw vertically, label each one of the axes properly, and also scale accordingly. Okay, you know, if this is 1, then that's 1, right? That's 2. Just make sure that the scale are appropriate. Okay. So now, if I want to do the addition, so what I will do is I will redraw this coordinate system. Okay, I label it as 1, 2, Okay. So now, to make it a little easier, I'm going to sketch both of the curve, okay, both f1t, f2t in the same graph at here. So f1t, which is this, f2t is this. So if I sketch both inside this graph, so this will be f2t, this is 1, 2, and that will be the f1t, right? So it's not very perpendicular, but you can use a ruler if you want. So this is basically f1 of t and f2 of t. Okay. So now I'm ready to do this addition. Okay. I could maybe, to make it a little easier, I'm going to redraw another coordinate system. Okay, right at the bottom. So to make it a little bit straightforward, the way I draw the one here is exactly the bottom. Okay. So if you can align basically everything, okay, together. So we're looking for f1 of t plus f2 of t. So that's the new function that we're looking for. How do we do that? Okay. When you add two functions together, basically you're adding all of the t values. So let's say, for example, you're adding, what is the negative 10 plus f2 negative 10? What is f of 0 plus f of 0? What's f10 plus f10? Right. So basically you pick any t value, you plug it into the function, then you add them together. Right? That's essentially what adding means. Okay, it's adding these things together. But graphically, if I look at this one here, anything beyond t equal to 0 or t less than 0, it's all 0 here, right? Anything beyond t equal to 2, it's all 0. So there's only something between 0 and a 2 at here. So when you sketch, you can start from t equal to 0. Okay? You can draw a vertical line, something like this. You look at this, at this arbitrary moment, you're adding this value and this value together. And this value is how much? It's 1. And this value is 2. So when you add 1 and 2 together, you get 3. And this applies to anywhere between where? Between 0 and 1. Right? So anywhere between 0 and 1, when you look at the curve, you're adding this portion and this portion together, which is a 3. So you can say 1, 2, 3. So you get 3 up to t equal to 1. Is that clear? Okay. And after t equal to 1, now you're adding this value and this value, which is 2 plus 0. So between 1 and 0, you get how much? 2, right? So from t equal to 1, there's a drop. It drops from 3 to 2, but 2 is kept until t equal to 2 seconds. And after t equal to 2 seconds, what will be the value? 0. So that dropped down to 0. So this is the function f1 of t plus f2 of t. That's graphically to show the value of it. Okay? Okay, I want you to practice yourself. Give yourself 1 minute. What's f1 of t minus f2 of t? So you can make use of the original, superimpose the two curves together, f1 of t minus f2 of t. Use exactly the same procedure. Got it? Yeah. So I'll do it, set it here, and you can verify if we're on the same page. Between 0 and 1, I'm using 2 minus 1, which give me 1. So that's between 0 and 1. Of course, outside it, it's all 0. Between 1 and 2, I'm using 2 minus 0, which is 2. So that actually goes up to 2 and back to 0. Okay. So the stair reversed, right? What about f1 of t times f2 of t? Let's do it quickly. Between 0 and 1, what times what? 2 times 1, which is 2. Between 1 and 2, 2 times 0, which is 0. So you back to 0. So basically, the whole curve is this. Okay, that's f1 of t times f2 of t. Next week tutorial, by the way, there's no tutorial this week. We'll have a tutorial next week. In the next week tutorial, the first one, they will review typical operations of functions such as shifting to up or down, left and right, scaling along the time axis, so either expand or compression, and combined together, right? Shifting and scaling combined together. So those are be covered in the first tutorial. Highly recommend that you go to the first tutorial, okay? And I talked to the other instructor. You may not have learned some of this in your high school, but we're actually making use of these manipulations, okay, for next stage of convolution concept. So, okay, so go to the tutorial next week. Any questions so far? So good? Okay, yeah. Okay, so now I'm going to get into a formal part of the lecture. The first part of the lecture is the first lecture, as I indicated, is introduction to signals and systems. Okay, signals and systems. This is a yes. Yeah. 1 minus 2. But this is f1 though. Yeah. Now this course, okay, is it's an introductory level course, including signal system plus differential equation. So it's a sort of mixed courses. But we don't go into too much of a depth about signals and the systems. Okay. A majority of the course will be on differential equations. Okay. Some of the course material related to system signals, such as what we're going to do now, and also like a Laplace, Fourier. So those are typical signal system concepts. Okay. Yeah. And if you're electrical, you will go much more depths about this concept. If you're mechanical and civil, this is maybe where, in terms of system signals, it will stop. So it gives you still a preliminary concept of what system and signals are. Okay. So first of all, let's put things together. Right. I think in the first class I have talked about system concept. You know, when you have a system where you can use a black box, okay, a rectangular black box to represent the system. A system has to have input. A system has to have output. Okay. So that's the first type of system. So for this system that I just sketched it here, I only have one input and one output. And this is what we call single input and single output system. SISO. In reality, there are a lot of SISO, but majority of the system, actually the next one, if I have a system number 2, and number 2 maybe you actually have multiple inputs. So I don't know how many, but there will be signals, so input signals, multiple inputs into the system. At the same time, and you can have multiple outputs for this system. So that's a typical, actual reality. Lot of systems just like this. You can put many inputs into the system, and the system produce many outputs. For this system, we call that multi-input and multi-output system. In short, MIA or MIMO system. When you are doing control, if you're going to graduate study in a control system, and often in time you're dealing with MIMO system. Okay. Yeah. Okay. So now you see the diagram that I just presented has both this concept of a signal and also the concept of system unit, right? So let's think about the signal first, and then let's talk about the system. Okay. Signal is a very simple word. You hear that almost on a daily basis. You go through a traffic intersection. What do you see? You see a signal lights, right? But that's not exactly the kind of signal we're talking about here. Okay. Now, if you read the Merriam-Webster, the definition of that is, it's a detectable physical quantity or impulse as a voltage, currents, or magnetic field strengths by which messages or information can be transmitted. Now this is more or less like what we're talking about here. Okay, so the signal. Some other alternative wording you may have heard about signal is, it's the energy, a traveling wave that carries some information, a function of time. So I actually like this one here quite a bit. The energy Okay. That's very much close to our natural sense, actually. So when we think about signals, we often associate the signal to time. You often think, okay, so at this time, what exactly is that value? At that time, what value would be the next? Right? So you look at the stock market, you look at your time elapse of academic performance. So those are very typical function of a time concept. Okay? However, a signal is not always about a function of time. Signal could be just a function of an arbitrary variable, okay? Not always the time. Okay? And signal can be continuous. Okay, can be continuous. And that's pretty much the case in reality. When I talk, when you hear, when you watch, everything that you have continuously sensed, they're continuous. But it can also be discrete. Okay, it can also be discrete. And this is the nature of the nowadays. The whole world, it's an analog, but on the back of it, we're trying very hard actually to use 1 and zeros to describe the world. Every digital equipment that you're using inside the signal processing is using discrete signals, essentially. Okay. So signals can be continuous, that's the reality. It can be discrete. Discrete is more of a things that human, artificially created. If I have a continuous one, I can sample it, I can get the discrete one. Okay. And this is basically, in real world, what it is. Okay. So that's something about the signal here. Okay. When you see the signal, you see x of t, y of x. So often in time, it can be represented using certain function. This is maybe cosine t. This is maybe sine, let's say, e to the power of x. And when you sketch them out, you get a signal, or you get a curve that representing this signal here. Okay. Okay. A system. Okay. Now this is a more complicated concept now. Okay. As I draw it here, you can see this is a system here. This is a rough representation of a system. So from the diagram, you can clearly see, right, a system the system has to take signals and also produce signals. Okay? Yeah. That's the nature of a system. Now there is a special case. So a system could produce signal without external excitation. And that's actually what we call basically an initial condition. So if the system initially has accumulated certain energy, and just like let's say when you pull a pendulum, right, to a certain stage, and you let it go, right? So what happens? This pendulum will start to move. Okay, yeah. So even though maybe you didn't input any force, any push, but the pendulum will still start because initially, right, there is this potential energy there, and it's enabled it basically to move. Okay. But the system had to produce signals. Okay. And the signal and the system are like basically so close to each other. Just signals are meaningless without a system. Okay. And likewise, a system is meaningless without a signal to produce. Okay. So that's the idea of a system right here. There are so many examples of a system. In electrical, you have learned a circuit system. So I'll give you maybe an RLC circuit. And here's the RLC oscillating circuits. And what do? In your experiment, you maybe give the system some kind of a voltage input. Right, so this one, let's call that a voltage input. So this is the input here. Given that input, you may be interested in what is the output voltage across this capacitor. Okay, that's essentially input, output, and then the system is this. Right, that's the box. In this case, it's a single input and single output system. Okay. Mechanical, I'll give you an example of a mass spring damper system. Let's say I have a mass, and the mass is attached to a spring at here and a damper. Okay. So this is a spring, this is called a damper. Spring is very easy to understand. You know, you see a spring many times. Damper is essentially, if you look at the doors of anyone in the classroom, when you open it, on the top of the door there's a hinge, right? That essentially is a damper. You know, it doesn't close or open sharply, abruptly. It gives you the slow motion, right? So there is a damping in it. That's called a damper. Okay. So this is essentially a mass. You consider the card, that's fine, attached to a spring and a damper. There might be a force, external force applied to this mass. And often in time, we'll be interested in, given this system, what will be the displacement behavior of this mass. Basically, we set up a system. Let's say if this is the initial stage, how does this mass move around in nature? We represent this displacement of this mass using x. So this x out of here is what we try to obtain. Or in this case, the x out of here is what we call what? The output. Okay. So here is the input, and here is your output. This is a typical mass spring damper system, and we will actually, a couple lectures will see how to model this system. So for this system here, for this system here, what will be the model for that system here? Okay. This brings us to a very important question in here. What do we mean by model, and why do we need a model for? Right? Yeah. So what is the model in here? Model is essentially a mathematical equation. It can be one equation, it can be a set of equations. It depends on the number of inputs and number of outputs of the system. Okay, so model or a set of equations. It depends on the complexity of the system. And this is the idea behind everything about the math. You're using math to describe the nature. Consider the system of the nature, and you're interested in the behavior of the nature. So how do I predict the nature? How do I describe the nature of the behavior? You got to be able to use a certain set of mathematical equations to describe that. Right? Okay. So model is a mathematical equation or set of equations to describe or even predict, okay, the behavior of the system. And this is the major part of the course, is we will learn the very preliminary or very fundamental approach, mathematical approach to describe the behavior of the system. And that starts from first order differential equations, second order differential equation, mostly it's about the linear, so it's an ordinary differential equation, right? So the behavior at here, okay, I use a very lay words called behavior, but more formal words for the behavior, okay, I can reword it as dynamics. And this is where the course name comes to picture, system dynamics. Right? The dynamics of certain system basically is the behavior of the system. Okay? It's a moving concept. Right? It's not a static concept. Okay? And often in time, of course, everything is about time, right? You know, you're talking about the behavior over time, you're talking about dynamics over time. So how do we get there? Okay, we have to get there slowly. Okay, but to get there, the first thing that I would do, okay, today, a little bit maybe today, and then the next few lectures is we'll look at, okay, first. We're going to look at the classifications of system. Okay. And we're also going to look at some properties of the system. So, what's the typical property of a system? And how do we typically classify system? Okay, that's what we're going to start with. Okay. This is where I will caution you things are going to go a little bit abstract, okay, especially the properties of the system here. Okay. So, what are the properties of the system? Let's start from property first. Okay. So the property of the system we're going to cover, okay, there are three properties we're going to cover. Number one is called causality. Causality. Number two, we're going to look at linearity. And number three, we're going to look at time invariance. Whether it's time variance or time invariance. So each one of the words has the opposites, right? Causal, non-causal, linear, non-linear. Time invariant, time variant. So that's we're going to look at the properties of the system. The three properties. In terms of the classification, in terms of classification, this is exactly what I just said actually. Classification basically means we're going to look at the causal and non-causal. How do we classify the system according to the property? Whether it's a linear or non-linear. How do we differentiate these two properties? And last of all, how do we differentiate time invariant and time variant? Okay. All right, and that's the steps that we're going to do. Okay. After we finish this, and then we'll get on to some signal manipulation and system dynamics concept. Okay, So we're going to tackle this first, right? The causality. Okay, so for causality, I need to be clear. There are actually two different concepts. One is signal causality. The other is the system causality. Okay, so let's start from the first one. Let's look at the signal causality. Probably that's what we're going to be able to finish today. Essentially, the definition here is causal signal. Okay. So we're talking about causal signals here. Causal signals are signals that are zero for all negative time. That's causal signal. Okay. So it's a signal that are zero for all negative time. Mathematically, to describe it, basically saying if I have a signal f of t, then it's going to be zero for the t that is less than 0. If you have a signal like that, then we define it as a causal signal. It's very simple, right? So let's look at examples here. Let's say I have a signal like this. Okay. This is f of t, and this is t. So according to definition, is this a causal signal or non-causal signal? It's causal, right? Because it's 0 for t less than 0. So this is a causal. Okay. However, okay, if we have a signal very much like this, except there's a hump over the left side here now. So now, because something exists when t less than 0, then according to the definition, this will be called a non-causal signal now. So that's what definition of signal causality. Okay, it's very straightforward. You just have to look at the t less than 0 part. Is there anything there? If there is nothing there, it's causal. If there's something there, doesn't matter, even if it's just one value, then you can call it non-causal. Okay. Okay, so that is the signal causality. Okay. System causality. So I'll start by an example first, and then I'll write down the formal definition. Okay. So let's say I have a system like this. The system input is f of t. The system output is called y of t. And the y of t, okay, is given as this. Okay, so y of t is given as y of t equal to f of t minus 2 plus f of t plus 2. Okay? Yeah. Now remember, now we're talking about time function. So this is a function of time, and this is a function of time. Function time basically means give me the value of this function at t equal to something. Okay. With t equal to 1 second, you get a value. T equal to 2 seconds, you get another value, right? That's basically what function of t means, okay, time. So let's take a look at this system right here. Right? Let's take a look at this system. And I'll forget about the concept first. I'll try to plug in certain t value into the output first. Okay? So let's say at t equal to 4. At t equal to 4, what is the output value of the system according to the given system? What will be the output of the system at t equal to 4? What do? Y of 4, that's right. Y of 4 equal to what in this case? F of 2. So maybe I'll write down the so 4 minus 2 plus 4 plus 2, which is f of 2 plus f of 6, right? Okay. So this is the results based on the given system. Output equal to at 4 equal to f of 2 plus f of 6. Now, can you interpret it? What does f of 2 means? F of 2 means what? It's the value of f at t equal to 2. F of 6 is value of f at, say, 6. And f is the input. So if I say it even more clearly, I would say this is the input at t equal to 2. This is the input at t equal to 6. But I'm looking for the output at t equal to 4. Now, did you see anything abnormal here? Based on what I just, so the output at t equal to 4 is given by the input at t equal to 2 and the input at t equal to what? 6. So what's so abnormal here? What's so non-normal? Come again? Excellent. That's the keyword. Future. Future here. So we're talking about t equal to 4. But the output here is what? You're looking at t equal to 6. So let's say right now is t equal to 4. T equal to 6 not happened yet, right? But I'm using what value to get the output? The future value to get the output. See, that's the so. Is that possible actually? First of all, yeah. Well, that's. Who said yeah? I'll be very much interested in that possibility actually. First thing I would dump to is maybe buy a 649 or something. So that's not possible, right? You cannot use future values to calculate the current value. Mathematically it's possible. Okay, mathematically possible, but in reality it's not. So this is the abnormal part that I was talking about here. Okay? This is actually an example what we call what? Non-causal system. Okay. So this system here, maybe I'll write down words here. Okay. So as you can see here, so output y depends on future input f of 6. Okay. That's the observation. So here we can see the system is non-causal. Okay, it's non-causal. So I'll give you the, maybe I don't have time, I'll give you the write down the formal definition for causality for system next. But now you actually can already a little bit summarize yourself now. If a system output depends on future inputs, then it is non-causal basically. Okay, as simple as that. Okay. All right, I'll give you the more formal one in the next lecture. I'll also go through a few examples of looking at the causal and the non-causal system. Okay. Any questions? Okay. We'll see you next week. These are the lecture notes. I'll post both. Yeah. Go to the tutorial next week. Okay, I'll see you next week.